So here is the derivation for an expression for the vapor pressure of a pressurized liquid. So it's also raining and it's also loud, so sorry about that. But that will just be in the background. So there are 4 steps to this derivation. The first one is to express the changes in chemical potentials that arise from the change in pressure. So essentially we apply pressure to a liquid gas system at equilibrium, and then we'll see how these chemical potentials change. We'll then equate these changes, assuming that equilibrium is maintained. We'll then identify the limits of integration and then carry out the integration. So essentially the setup of the scenario is that you have a piston here, 2 phases. Bottom phase is a liquid, top phase is vapor. This is a movable piston which can apply a force at delta P. So at equilibrium, there's going to be a vapor pressure, or the pressure of the molecules wanting to escape into the gas phase, and as a result that's the pressure. And then there's also pressure here from the atmosphere or otherwise by the piston, which is applied onto the liquid. So this is the pressure that the liquid experiences, and this is the pressure from those gaseous molecules which escape the liquid of the molecule. So our first assumption, as stated earlier, is that we are at equilibrium. So what this means is that it's just as favorable for the molecule to be in the gas phase as it is to be in the liquid phase. What this means is that the chemical potential of the liquid phase is equal to the chemical potential of the gas phase. This makes sense because the chemical potential essentially is a variable which kind of refers to the likelihood of change, or the potential to change, while chemically in this case, while in that phase. So because it's just as favorable to be in liquid or the gas phase, these two will obviously be equal. So say we apply a pressure, delta P, there will also be a change in the chemical potential of the liquid phase, which must equal the change in the chemical potential of the gas phase if we're to remain in equilibrium, and that's why this equality is necessary. So while we have this equation, what we really need is to describe this chemical potential value in terms of a change in pressure, since that's what we're doing. We're changing pressure. So it's helpful to refer back to the equation. Partial pressure gives free energy over partial pressure at constant temperature is equal to the molar volume. We know that dg is equal to d mu for one compound, for one element sort of molecules. So here we can get 2 more equations. So the delta mu, the liquid, over the delta, remember that capital P refers, or is related to liquid, right? Because that's what the pressure of the liquid experiences. So I'm going to put a capital P here. At constant temperature is equal to the molar value. Likewise, delta mu in the gas phase over partial pressure at constant temperature is equal to the molar volume. So here we can kind of solve in terms of the chemical potential value, so I'll show you that real quick. I'm also going to assume that it's no longer partial, but refers to the entire equation. So chemical potential, the liquid form is equal, at constant temperature, is equal to the molar volume times d capital P, or the pressure experienced by the liquid, or total pressure experienced by the liquid. Solving in this side, delta mu G is equal to the molar volume times the change in partial pressure. So remember that lowercase p corresponds to a gas. So our second assumption that we want to make is that we want to assume that this gas is a perfect gas. So we can use the perfect gas law. So here we know that PV is equal to nRT. Furthermore, P molar volume is equal to RT. So molar volume is equal to RT over partial pressure. Now we can plug this in right here, and then we can get the equation change in mu. The gas phase is equal to RT over P dP. So we've completed step 1. We've expressed the changes in the chemical potentials that arise from the change in pressure by using these relationships. We also simplified by making the assumption that we are dealing with a perfect gas. So the second step is to equate these changes with each other. It's pretty simple. Just to reiterate, the change in the chemical potential of the liquid is equal to the change in the chemical potential of the gas. Now we want to plug in the prior equations. So mu L is equal to, or d mu L is equal to molar volume times the change in applied pressure, the pressure experienced by the liquid, is equal to this value, RT over P dP. So we have this. That is step 2. Now we want to identify the limits of integration. So we want to do this in a way that will get us limits for this d capital P term and this d lowercase p term. So this capital P term corresponds with the liquid. It corresponds with the liquid, and this lowercase p term corresponds with the vapor. So let's do the vapor first, since it's a little easier. So the initial condition and the final condition. So the initial condition that we want to integrate for in terms of vapor and partial pressure is P star, where P star refers to the vapor pressure at a standard condition. So by standard condition I mean 1 bar, no applied pressure, pure molecule. So P star. The final will be P after the applied pressure, and then yeah. So in terms of this liquid integration limits, we're going to want to establish an initial and final. It's a little harder to think about here, but if you remember from the picture, you can see that initially there is a pressure P at equilibrium which opposes this vapor pressure. So at equilibrium, at standard conditions, we'll see that this P value, capital P, is equal to this P star. Right. So what we also know here is that the vapor pressure is equal to P star. Okay. So in the final condition, after we've applied this delta P, we'll see that both P and P change. So what we want to equate here is that this P final condition is equal to the initial P, so the vapor pressure, plus this change in P, because we're at equilibrium. So these are sort of our limits. Since in like reality, it's sort of hard to find this p-value. Usually what you want to do is you want to assume that p is equal to p star. This is based on the assumption that the vapor pressure does not change much due to the applied pressure, or the change in pressure. So this is going to change into P is equal to P star plus delta P. Alright, so now we have our limits. Just plug in these values, P star and then P star plus delta P. So now we have our limits of integration. Let's copy down this formula. Molar volume times d change in P is equal to RT over partial pressure dP. Okay, now we want to integrate. Move this over. Okay, remember here, capital P, that refers to the liquid. So we have our P star, it's our initial, and our P final is P star plus delta P. Here we have our vapor limits of integration. This would be the P star, it's also the initial, and the final is P. Okay, so step 4. We've identified the limits of integration. Now we carry out the integration. So there's another assumption here that we wanted to make, and that is that this this Vm value, which is actually the molar volume of the liquid, does not change due to the applied pressure, or something like that. So that allows us to pull it out of the integration. So let me just rewrite that real quick. The molar volume liquid times the integration of P star to P star plus delta P dP is equal to the integration of P star to P RT over P dP. While we're at it, let's pull out this RT value too, and then move all of the variables to one side. So that will allow us to end up with the following equation. RT, and then just divide by this molar volume of the liquid times the integration of P star to P after the applied pressure, dP over P. So these integrations are pretty simple. You'll have delta P, so just P final minus P initial on this left side. So P star plus delta P minus P star is equal to RT over molar volume of the liquid times the natural log of P final over P initial, P star. So this simplifies to that. So now we have this equation. Okay, so essentially we want to solve for this value. So we want to rearrange it in a way that allows us to do so. So just divide by this. That's P times molar volume divided by RT is equal to ln of P over P star. Okay, now we raise to the power of E, so P star is equal to E to the power of change in total pressure times the molar volume of the liquid divided by RT. And then finally P is equal to P star, or the vapor pressure of the pure molecule, multiplied by E to the power of delta P, change in total volume, times the molar volume of the liquid divided by RT. And this is the final equation of an expression which relates the applied pressure, delta P, and its effect on the vapor pressure. So we have our vapor pressure expressed in terms of delta P. So this is the final expression.